When we first learn how to investigate motion, we usually start by focusing on motion that is restricted to one dimension, or 1D. For example, we talk about cars that are heading east or west, or a person that is jumping up and down. Of course, in the real world, motion doesn't tend to be restricted to a single dimension. We live in a three-dimensional universe, after all. Before we jump into 3D motion, though, let's take the next step and look at motion in 2D first. It turns out that 2D motion is pretty common. Most of the motion that we're familiar with in our day-to-day lives can actually be approximated as 2D motion. Think about your drive into work or school today. While you probably took a somewhat complex path to get from home to the office, that path was probably mostly confined to the north, south, east, and west directions, or the horizontal plane. Unless you took an airplane to work, most likely very little of your motion was directed up or down. That same reasoning applies to lots of different systems. In order to be able to analyze the motion of an object that is traveling in 2 dimensions, you might think that we need to learn a bunch of new equations or write ones that we've learned down in some strange way. But in reality, we can just apply the exact same definitions that we've learned, we just do it separately for each direction of motion. In some way, this is what makes vector quantities so useful. Whenever we are dealing with 2 or more dimensional motion, vectors allow us to describe the important quantities using a single quantity instead of 2 or more. But hidden within those vector quantities is information about the motion in each of the individual dimensions. Let's take a look at an example. Let's say that you are standing at the top of a cliff and you throw a rock horizontally. After you release the rock, it is going to start accelerating towards the ground. The path that the rock makes between your hand and the ground is a parabola, so we might think that it's going to be difficult to analyze this motion since it isn't just a straight line. But, and this is important, even though the object is traveling along a 2-dimensional path, the motion can be reduced to 2 independent 1-dimensional motions. We already know how to solve 1D motion problems, so solving 2 of them shouldn't be a big deal. So how do we do this? Well, let's think about the motion of the rock after it leaves your hand until just before it hits the ground. Specifically, let's talk about our motion quantities, displacement, velocity, and acceleration in the horizontal and vertical directions. We can see that the rock travels some distance in the horizontal away from its initial position, so it has a displacement in the x direction. Sometimes this is referred to as the range. Since the rock falls to the base of the cliff, it must also have a displacement in the y direction. Also, if you start by throwing the rock in the x direction, it must have some velocity in the x direction, otherwise it wouldn't be moving horizontally at all. But since its motion is initially only in the x direction, then at least at first, the rock's y velocity must be 0. Finally, if we ignore air resistance, then there's nothing causing the rock to speed up or slow down in the horizontal direction, so the x component of the acceleration must be 0. However, gravity is pulling the rock downward, so the y component of the rock's acceleration must be equal to minus g. Remember, the acceleration tells me about the change in velocity, so if the rock has no acceleration in the x direction, then its velocity can't change in that direction. For its entire flight, the rock's velocity in the x direction has the exact same value. It's constant. However, the rock is accelerating in the negative y direction, so we know that the y component of the rock's velocity must change. So at this point, we have a general idea of what the motion of the rock is going to look like. We've separated the 2-dimensional motion into 2 independent 1D motions. But there's only one rock, so something must be linking these 2 1D motions together. Well, that something's time. We're only dealing with one object here, so the time it takes from leaving your hand to hitting the ground is just that, no matter what approach you take to actually solving for the motion. This is important because even if we are trying to solve for a quantity that only seems to depend on one direction, for example, the rock's range, we might need to solve for time using the other direction. Alright, so we know that we can talk about the motion of this one object by breaking it up into 2 1D problems. So how do we actually do the solving? Well, there's quite a bit of information here, so the first thing to do is make a list of the quantities that we know, and those that we don't in each direction. In the x direction, we know the initial velocity of the rock is 10 meters per second. We know the rock is not accelerating in the x direction, which also means that the final velocity of the rock is also 10 meters per second. We don't know the displacement of the rock, that's what we want to solve for. But since the displacement is independent of my choice of the origin, I can put the origin wherever I want, so I'll place it such that my initial position is 0. If you look closely at this list, you can see there's very little information here. The only useful information that I have is the initial x component of the velocity. I can't use only that to find the range. So I need to use the information I've been given about the y direction. In the y direction, I know that the initial velocity is 0, but I don't know the final velocity. I know the acceleration is negative 9.8 meters per second squared. Based on my choice of origin, the rock's initial position is 20 meters and its final position is 0 meters. Now I have some information that I can actually work with. So in order to solve this problem, I need to use the information given in the y direction to solve for time, and then use the time plus the information I have in the x direction to then solve for the range. So the final question is, well, how do I solve these things? Well, we've done that before. Since we're dealing with two 1D constant acceleration problems, we can just use our kinematic equations. The same equations that apply to 1D motion work here too, since all we are doing is 1D motion. We're just doing it twice.